Hello everyone, in today's class and video we're going to talk about optimization. So first of all, I'm going to introduce you some concept. What is local maximum and the local minimum? So F has a local maximum at A if f of A greater than all of fx for all x near A. Similarly, f have a local minimum at A if f of A is less than all of the fx for all x near A. What does that mean? Let me use B. Maybe B is easier for you to separate them. B for all f of B nearby B. So if you take a look at this graph, okay, so our local maximum is here. This is our A, and our local minimum will be here. This is our B. So for all of the x nearby A, so that means in this part nearby A, f of x, which is here and here, is less than f of A, because at this point is A and f of A. So for the local minimum is B, f of B, for all of the x nearby B, which is here nearby, and then the f of x is less than all of them are greater than f of B, then we call it its local minimum. So why we are called local? Because hey, if you look at this point, the point that I label in blue, they're probably greater than f of A, but this is not the definition of local maximum, because you can see the number nearby that blue point, such as, I'm going to highlight it in yellow, this part is greater than the blue point. Let's say the blue point is C and the f of C. And we can find x in here is greater than f of C. So that's why this is not a local maximum. Local maximum doesn't have to be absolute the biggest number. It just have to be relatively biggest number. So the process of finding the maximum or minimum is called optimization. Okay, so a point in a local max or local minimum, usually local maximum, if it's higher than all of the nearby points. Similarly, if you're finding a local minimum, which is our FB, it should be lower than all of the nearby points. Remember, it's the nearby points. Okay, so for local maximum, so we talked about local maximum. What about global maximum and global minimum or global extreme? So by the definition, F has a global maximum at A if f of A greater than or equal than fx for all x in the domain of f. So what does that mean? So the keyword is all x. So that means if I give you a graph like this one, it ends here, let's go up, and ends here. So where is your global maximum? should be this point. This happened also to be a global minimum. Let me draw another one that tells you that hey, global maximum doesn't have to be global minimum. It could be, but sometimes it doesn't have to be, such as this one. And the ends here, that's the end of the domain. It's not extension, so that's why you don't see the arrow point. So here, this point, f of a, and f of a is our global maximum, because all of the x in the domain, which is everything in the domain of f, is less than f of a. So that makes it a global maximum. So that means if you find a random point on this graph, like this one, is less than f of a, this one less than f of a, every random number that you find is less than. So the difference between the local one is the local is for all the nearby x, but for the global maximum is all of the x. So this is similar to global minimum. So global minimum is at b, let's say b, if f of b is less than all of the x for all of the x in the domain of f. So in this case, this is our b, and f of b, as you can see, f of b is lower, it's the lowest point in this graph. So f has a global extreme if at a, if f of a is a global maximum or minimum. So some places you would say absolute instead of global. So in here, these 2 points is going to be our extrema point. Okay. So now let's take a look at this graph. So here we have a couple points. So this one is our local minimum, and this is our local maximum. This is also local minimum, and this is local maximum, also global maximum. This one is the lowest point of the graph, so this point is global minimum. As I told you before, global minimum can be one of the global minimum point, but it's not necessary. Sometimes it could be the end point. Okay, now I'm going to show you an example. So the table shows an annual calculus enrollment at a large university. Which year had the local maximum or local minimum calculus enrollment, and what were the global maximum and the global minimum in calculus? Well, I think the easiest one to find is we can find the global maximum and the global minimum first. So let's take a look. Which point gives you the lowest enrollment? So it should be at year 2000 is the local minimum. It got the lowest, it has the lowest enrollment with 1,257 enrolled in calculus class. And now what would be the global maximum? Well, it seems like in 2007, it has the highest enrollment in the calculus class with 1,582 students enrolled in it. So what about the local maximum? Well, the global maximum is in 2002 and 2007. The local maximum is in 2002 and 2007. Because by the year nearby 2002, like 2001 and 2003, 2002 is the highest year. All the number nearby, the year nearby, the enrollment nearby, the year before, the year after is smaller than 2002. So similarly to 2007. And then the local minimum is in 2003 and 2009. Because nearby 2003, which is in 2002 and 2004, they're both higher than 2003. And similarly to 2009, because in the year of 2008 is less than 2009, and also the year in 2010 is less than 2009. So that gives them a global minimum. So now another definition is critical number. So the definition of a critical number is for a function f is a value x equals to a in the domain of f where either the derivative of fa equals 0 or f of a derivative is undefined. In that case, we call it the critical number. A critical point for the function is the point is a point where the critical number at, which is a f of a, where a is the critical number of f. So here's two definitions. So this gives you what? Well, think about when does the derivative is equal to 0. It's when you have the tangent line is horizontal, right? So if the tangent line is horizontal, that gives you what? Either a local minimum or local maximum, right? So we can use the critical point to help you to find the local minimum or local maximum. So now let's give some example, and I want you to find the critical point, find all of the critical points of this function fx equals to x cubed minus 6x plus 9x plus 2. So we know that the critical point occurs at when the derivative is equal to 0. So the first step is we can try to find the derivative of this function. So I have 3x squared minus, I think this 6x. So I have a 12x plus 9. And then the critical point occurs at when the first derivative is equal to 0. So I have 3x squared minus 12x plus 9 equals to 0. When I solve that, use AC method, pull out the 3, I have x minus 1 and then x minus 3 equals to 0. So the critical number would be x equals to 1 or x equals to 3. So, and remember, the critical point is you still need to consider that, hey, when f, the first derivative at a, is undefined, well, since in here for all of the x are all defined, so there's no places that where the derivative f of prime is undefined because there's no restriction for that domain, so that we find the critical number at x equals to 1 or x equals to 3. That's the critical number. We still need to find the critical point. So the critical point is you substitute the number into the original function to find the y coordinate, which is 3 minus 12 plus, which is 1 to the cube minus 6 times 1 plus 9 times 1 plus 2. So this is equal to 6. Similarly, f of 3 equals to 2. You can calculate that by yourself. So that gives us a critical point when x equals to 1, y equals to 6. When x equals to 3, y equals to 2. So remember, this one is critical number. We use the first derivative to help us to find that. And this is critical point. That means you still need to find the y coordinate of this point. So this point will help you to find the local, remember it's the local extrema, not the global one. So apparently this number is bigger and this number is smaller. So can I say this is a local maximum and this is local minimum? Well, not yet, because if you remember this graph, sometimes your local minimum can be bigger than the local maximum, right? So we can't just judge by the number and decide, hey, this is local maximum and this is local minimum. We can't do that. So what do we do to find the local minimum and local maximum? One way to do it is by the definition. If you remember, we talked about that by the definition. If you have to be local maximum, the number nearby you has to be less than the local maximum, which is, let's say, f of a has to be greater than or equals to all of fx for all x nearby. And similarly to local minimum, if you want to be a local minimum, the number nearby you has to be the smallest number. So that means, well, now I found 1. Okay, maybe I can test out a number on the right and one number on the left. So try to find out what is 1.1 equals to. Well, let's find out. F of 1.1, which is I'm trying to find the number on the right side nearby the critical point. And see this is equal to what? And in here, this is equals to, and then I calculate by myself, this is equals to 5.971. And then you also need to calculate, hey, this is 0.9, which is a number on the left of 1 equals to what? And then if you put into calculator, this is equals to 5.969. They're both less than 6. So now we can say, hey, this is the global maximum. Well, you do the same trick. For x equals to 3, you need to find out, hey, x 3.1 is equals to what? Or x 2.9 equals to what? Are they both greater than 2? If they are, then I can say, hey, this is our global minimum. So now, after we found the global minimum and global maximum, local minimum and local maximum. Now let's try to figure out, hey, does this function have a global minimum and global maximum? Well, I'm going to erase this because this is not the graph of the function. So for this specific function, do we have a endpoint? So since the domain doesn't have restriction, we didn't say, hey, s is in between 1 to 10, so there's no endpoint. Since there's no endpoint, so most likely the graph can go as high as they want. Probably the graph look like this one. So in that case, there's no endpoint that we can say there's no global minimum or global maximum. Okay, so now this is one way. Earlier we just introduced a way to calculate the local maximum and local minimum by plugging the number nearby. So now let's think about, is there an easier way to do that without just plugging the number multiple times? Well, another way to do it is use the second derivative. So when you take a look, what does a minimum look like? A local minimum and local maximum. Well, if it's a local maximum, the graph is going to be what? Concave down. If the graph is concave down nearby that point, then we will have a local maximum. And then in here, similarly, concave down, then we have a local maximum. Similar idea, if this is concave up, then we will have what? A local minimum. So what determines is it concave up or concave down? Well, that determined by the second derivative, right? If the second derivative which is f double x is less than 0, a negative number, then the graph at x equals to, let's say, a, is concave down. If the second derivative at b is greater than 0, then the graph at x equals to b is concave up. This is second one to do it. So the third way, let me write this one. The first way is you test the point nearby, which is what we did earlier. This is the first method. Second method is we use the graph, which is second derivative, to test it. Okay, so what's the third method? Again, let's take a look at the graph. If I have a graph, look like this one, and this is my local maximum, and this point B is my local minimum. So what happened nearby this point? Well, as you can see, the graph is going up and down, then you will reach a local maximum. You go up first and go down later. So that means for all x less than a, which is on the left side of x, this part, if the first derivative of this x is greater than 0. If you're increasing, that means your first derivative has to be greater than 0, because if you're increasing, you're going to have a positive slope of the tangent line, so that means you're going to have a positive number. Then you will have a first derivative is positive. And also, for all of the x, let me use for all, this is math notation. for all x is greater than a, which is on the right side of a, which is this part, and then all the derivative is less than 0 because it's decreasing, then we can say, hey, at a, this is a local maximum. So we can use the similar trick for b. For every number on the right side of b, for all x is less than b, no, I'm sorry, on the left side of b, we have the first derivative, since it's going down, so that means the first derivative is going to be a negative number because the slope is negative. And for all x on the right side of b, and the first derivative is positive because, and then you're going up, then we will have f of b is our local minimum. I forgot to say that f of a is local maximum if. Okay. So now let's go back to our early example. In the early example, use method 1, we test, hey, f of 1.1 and the f of 0.9, they are both less than f of 1, which is equal to 6. Then we say, hey, this is local maximum. Now let's try to use our second method, which is use the second derivative to check the concavity of x at 1. So we have the first derivative equals to this one, and now our second derivative is equals to what? 6x minus 12. And now we plug in 1 into the second derivative. We have a 6 times 1 minus 12, which is negative 6. So this is less than 0. If it's less than 0, that means at x equals to 1, the graph concave down. So that means what? If it's concave down, like we talked about in here, if it's concave down, that means f of a is local maximum. We can use the similar idea to test, hey, if our second critical point is local minimum or not. Second critical point is when x equals to 3. So now we plug in x equals to 3 into our second derivative. We have 6 times 3 minus 12. I have 18 minus 12, which is 6 greater than 0. So that means at x equals to 3, the graph concave up, like here, similar to here. So if it's concave up, that means I can say, hey, the point 32 is local minimum. Okay, so we already learned all of the method. The method 3, I feel like you can do it by yourself. All you need to do is just plug in 1.1 for the first derivative to test, hey, if 1.1 is negative, and then plug in 1.9 for the first derivative, see if it's positive. If that's the case, that means the graph is going up and down. That gives you a local maximum. If you forgot all of this, just draw a graph. It will help you to visualize how the concavity change or how the graph increase and decrease. Okay, so now let me have an example. If I given you a function, I want you to find the global maximum and the global minimum of this function. So as you can see now, we have our endpoint. So, right? So probably the global maximum or global minimum will happen in the endpoint or the critical point. Because sometimes if the graph look like this one, okay, your endpoint definitely is going to be your local minimum or local maximum. But what if the graph look like this one? So the endpoint doesn't guarantee you a global maximum. So that means we still need to find the critical point and check if this is the global maximum or global minimum. Okay, so let's find the critical point first. To find the critical point, we need the first derivative. The first derivative of that function is x squared minus 6x minus 9. And then let this equals to 0. I got x equals to, oops. Okay, so this is equal to 0. So I have x equals to -1 or x equals to 3. So this is going to be your critical number. And now we need to find the critical point by substituting -1 into the function. I'll get this is equal to 10, and then f of 3, you substitute 3 into the function, I have a -22. So that means I have 10, -22. And now after we check the critical point, I still need to check the endpoints because, like I say, the graph I have earlier, sometimes global maximum occurs at the endpoint. So the endpoint is -2 and 6. We substitute -2 into the function, I got 3, and 6 into the function, we got 59. So now with all of these numbers, we can easily to see, hey, this is going to be my global maximum. And this is our smallest number, which is our global minimum. So that means the endpoint, one of the endpoint is our global maximum. And one of the critical point, which is the local minimum, is happen to be our local minimum. Okay, so now let's recap how to find the global minimum or global maximum. If you've seen a graph, the first approach is you need to make sure that, hey, the graph have an endpoint. If there's no endpoint, like this graph, you might not be able to find global minimum or global maximum. So if there is an endpoint, you need to check the value of these two endpoints. And then all of the value of the local maximum and local minimum, which means you need to check all of the critical points. Okay, so that's it for this class. Let me know if you have other questions.